So we covered most of the important stuff for linear equations, how you solve linear equations, what you do with different types of equations, linear spaces, which is very important part, linear combinations. All of that is used also in eigenvalue decompositions. And this is practically second most important problem in linear algebra after solving a system of linear equations in general. So we will talk first of all about intuition behind that idea of eigenvalues, and hopefully you've heard about it before. And this is not the first time you hear about eigenvalues, but it's not too complicated to learn. So I will provide the theory, like how you compute by hand basic things, but nobody computes that by hand, too difficult, unless you have like matrices of 2 by 2 or 3 by 3. All right, so we'll also learn about numerical methods to compute eigenvalues. And this is an extremely important problem. It's used in controls, it's used in physics, it's used in everywhere. And here's the motivation for eigenvalues. Why do we need that kind of thing? So we can think about multiplication of matrix by a vector as applying some sort of transform or operator to that vector, which is scaling that vector and rotating that vector somehow in n-dimensional space. So thinking about particular vector as 2-dimensional, 3-dimensional, but you can do the same thing for n-dimensional. And then you multiply that vector by matrix, you get another vector, obviously. Okay. And this vector will be different from the original vector. Okay. So the question becomes, is there any kind of vector which is not changing the direction, but only scaling when you multiply that by matrix? So you have given matrix A, whatever it is. You are looking, so each vector will be somehow scaled, maybe like opposite direction, maybe same direction, different angle, different size. Okay. So is there any vector which you multiply by that matrix and it just stretches or squeezes or changing direction, but not changing the angle, not moving anywhere? Okay. On the same line, on the same direction. Okay. Is there any vector of that kind? So we will call that eigenvector if it is not changing direction, and it will have associated eigenvalue, which means scaling of that original vector, by how much you will actually scale that vector. And this eigenvalue might be positive or negative, so it could go opposite direction on the same line, it's kind of negative eigenvalue, or if it is positive, it will be scaled in the positive direction. Like if eigenvalue is 2, you practically scaling it by 2, that vector. So this is the overall idea of eigenvectors. So this will be how much it's scaled, it will be eigenvalue, and you preserve in the same direction, which means you practically, instead of multiplying by matrix, you can multiply that by a number. Much easier, right? So that's why this problem is so convenient and useful for many different things. You replacing mapping by a matrix by multiplication by a constant. Much easier, right? Yes.
So you mentioned the negative eigenvalues as going in the opposite direction, but doesn't that contradict the first one, which says it's not changing its direction or changing to the opposite direction?
So by direction, in 2-dimensional, 3-dimensional spaces, negative direction is different direction. But in the case of linear algebra, it's kind of same direction because it's sitting on the same line. So I might need to clarify here that it's the same direction or opposite direction, okay? But on the same line, subspace, same subspace line, all right? So it could flip the direction.
As long as it's on the same.
It's like positive or negative direction, but same, not different angle, not steering to a different angle, okay? So angle could be like 0 or 180 degrees, that kind of thing, okay? So this is used everywhere. PCA, have you heard about PCA, principal component analysis, which is used for dimensionality reduction for data sciences everywhere. Like if you have 500 variables and you need to train your machine learning algorithm or whatever, you don't want 500 variables, you want 5 or 10 most important ones, because most of them will be correlated. You don't care about them. You don't want to overuse same things. You don't want overfitting to your problems. So you're using much smaller subset of variables converted into PCA space. subspace. And then you're dropping everything else. You're looking for most explanatory variables, and this is what PCA does. It looks for the most explanatory variables in your subset, right? And then you can have much less variables. You don't need all of them. Most of them will be just noise, practically. You don't care about. Google PageRank. This is how Google makes web page searches, okay? It's building some graph. It explores the graph with PageRank algorithm, and this PageRank algorithm is based on eigenvalues. You have state space control, where you have matrices representing dynamical system. You have iterations on the dynamical system. Eigenvalues of that matrix of state space representing that thing are eigenvalues and poles of the system. So poles are eigenvalues, which is very convenient. So if you learned control systems and you learned about poles, so poles are eigenvalues of the system. All right. If you never learn controls, there's nothing to you, but that's fine. Okay. You have many other problems, like how you recognize faces based on the database of other faces. So you want to represent faces in particular order, in particular shape, and you want to combine them as linear combination of other faces. And for that, you're using eigenvalues to figure out which faces need to be represented. And eigenvalues tell you practically intuitively how much you stretch the space in different directions. So if you have eigenvalues very close to 1, it's not stretching the dimension too much. But if it is like 500, you're stretching a lot. And if you're thinking about, let's say, what happens to sphere, you can think like how much that sphere, hypersphere is stretched in each one of the dimensions of that hypersphere by eigenvalues. And you will see something which is also very related to eigenvalues, which is called singular values. Kind of for symmetrical matrices, it's square root of eigenvalues, but it's much more generic, and it works not only for square matrices, but also for rectangular matrices, which is very convenient. So this is practically a tool which is used everywhere in any single application related to linear algebra in any way. So singular values are very important, and they are related to eigenvalues in a sense. It's also telling you how much you stretch the space in a sense. If you're thinking about system of coordinates, matrix A is changing the system of coordinates. You're doing some sort of mapping of vectors. So it's kind of squeezing the axis, doing all kinds of rotations of the axis. Eigenvalues will tell you how. And you'll get only n eigenvalues from n by n matrix. All right, so it will tell you n directions. Okay, so let's see more specifically numerically how this works. Okay, so matrices practically rotate vectors and scale vectors. So if you have some particular vector, which is 2, 1, and you have some given matrix 0, 3, 2, 1, whatever that matrix is, you can write it as combination, linear combination of columns. So first coefficient is like 2 times the first column plus 1 times the second column, you will get 3, 5. So from that vector, you get vector 3, 5. Okay, you got that vector as 2, 1, and then you rotate it and scaled it to get the red vector. Okay, and eigenvalues and eigenvectors are different. You are not rotating it anymore. It looks in the same direction or opposite direction. Okay, so this is the type of vectors that we are looking for. And as example, vector 1, 1 of that matrix is eigenvector of matrix A. Why? Because if you multiply by that particular vector, that same matrix, you get practically 3, 3. So 3, 3 is obviously proportional to 1, 1. It's like coefficient 3. So 3 will be that scaling factor, which is eigenvalue. Yes.
So the eigenvectors, they are all within the column space of A.
Eigenvector?
Eigenvectors parts of the column space of A.
The column space of A, yes, they are, but it's not specific to eigenvectors. It's like any vector could be represented, like any multiplication of matrix by a vector could be represented in column space of matrix A, including eigenvectors. So it's not special for eigenvectors in that case. It's like all vectors that you would get from multiplication by a particular matrix. And we've seen that upper subspace of column space of matrix A, if you remember those 4 rectangles diagram. So all vectors are going into the upper right rectangle, because from any place here, when you multiply by matrix A, you get them all in column space. Because by definition, it's like linear combination of columns of A. That's what multiplication by vector means.
So it's like within all the column space of A, we are finding
You have a few
vectors
you have
that do not
a few vectors which are not changing direction. Yes, this is how you can look at it. All right, so the eigenvector here is 1, 1, and eigenvector is 1, 1, and eigenvalue is 3, which is a scaling factor. Now, how about other vectors? So obviously you can compute that by hand. I will show you some examples, simple examples. Again, you don't need really to learn the technique too much because this is regular linear algebra. We'll talk about numerical linear algebra, but you have other, and you can use MATLAB command eigenvalue, of A to get that all of the eigenvalues, or if you're using like that kind of specification, you get matrix of vectors and you get also matrix of diagonal values, which are eigenvalues. So it's a little bit different. I will explain in a second. So this is the second eigenvector of that same matrix. Typically you have like for matrices of n by n, you get n eigenvectors. Some of them might overlap. Some of them might be the same, but you cannot get more than n. You get up to n eigenvectors and up to n eigenvalues. Depends on the dimension. And matrix should be square n by n. All right. So pay attention to that MATLAB command E equals the first one, eig of A. So this gives you vector of all of the eigenvalues. One of them will be 3, for example. Second one, I don't even know what that is, but it will give you 2 numbers, vector of 2 numbers, okay? Second command will not give you that vector. So if you want only eigenvalues, just use the first command separately, okay? Second will give you 2 matrices. First matrix will have columns, and each column will be eigenvector. Each column in the second one, not each column, the diagonal values in the second one, in the D matrix, will be eigenvalues. The first is eigenvector matrix with columns of eigenvectors. Second is diagonal matrix with all of the eigenvalues sitting on the main diagonal, okay, corresponding to this particular eigenvectors in matrix V. So different kind of representation, okay? You can represent eigenvalues as diagonal matrix or as a vector of numbers on the main diagonal. Okay? You can convert one into another, but it's just additional commands that you need to do in MATLAB. All right, so these are MATLAB commands to get all the eigenvalues. All right, another important thing about eigenvalues in general. You have always infinite number of eigenvalues, which means if you solve that system of equations that we'll see in a second, and you get only one possible solution, something like invertible matrix, it cannot be true. You made some mistake in your computations, okay? Eigenvectors are defined up to a constant. So any constant multiplied by that vector still will be eigenvector. And this is obvious because if you multiply by a constant, you're not changing direction, right? So all of them, like any vector multiplied by any eigenvector multiplied by any constant will be still eigenvector. So there is way to normalize it somehow. You have 2 ways to normalize it. We'll talk about that in a second. So as I said, they are defined up to a scale, and convention is to normalize them to norm 1, which means the overall norm of that vector will be 1. To do that, you just dividing by norm of that vector. Each element you divide by norm of that vector itself, and then you get total norm 1, as we've seen probably like 4 or 5 lectures ago. And second way is to normalize by maximum. You're just dividing by maximal element in that vector, so the maximal number will be always 1, and other numbers will be less than 1, magnitude 1. It could be positive or negative, it doesn't matter, it's just maximal magnitude, okay, biggest absolute value of the elements of that vector will be 1, right? It could be negative 1 or positive 1. So these are 2 ways to normalize vector if you want particular vector, okay, single vector. But technically you can have infinite number of vectors. That's how it works. It's entire set of vectors. All right, so how you compute that? And a few more additional definitions here. So if you have matrix, square matrix, n by n, all the eigenvalues are defined as solution for that kind of equation. So you solve an equation AXI, which is A matrix A multiplied by that eigenvector Xi equals eigenvalue, which I'll call Si. Typically, people call it lambda in different kind of textbooks for multiple reasons. I call it Si for very particular reason, because in control systems, it will be Laplace variable, which is pole of the system. And we always use in transfer functions S variable, Laplace variable. So I'm used to S instead of lambda, but you can use lambda, same thing, right? Is it clear what I'm saying? It's just notation issue that you will see in most textbooks, that this is lambda I instead of Si. I'm using S. So it's eigenvalue times same vector, which means I can replace multiplication by matrix. Instead of that, I'm using number times same vector, just scaling it, because this is eigenvector and eigenvalue, all right? So the set of eigenvectors associated with that eigenvalue Si will be called eigenspace. Again, this is linear space, linear vector space of all of the possible eigenvectors, all right? And it always will be linear subspace of overall n-dimensional space, all right? And prove it technically, okay? So this is eigenspace. So another description here is that set of these values, and you'll have all kinds of like S1, 2, 3, 4 through n. Some of them, again, may overlap, so you might have multiplicity of these values. It's called spectrum, which is interesting not to mix with the Fourier spectrum, but they have very interesting relation between them. It's still actual spectrum, and they have relation to frequencies, because eigenvalues might be complex numbers. Typically, they are complex numbers, okay? So if you're thinking about complex number, they have magnitude and phase. And on the imaginary axis, you can think about that as j omega, and omega is frequency, okay? So practically single complex number tells you frequency and magnitude, which would be the imaginary part of that complex number and absolute value of that complex number. So it is spectral representation in a way, and depends on where your location of poles or eigenvalues is, you can know spectral response of a system, let's say, as one example. You can build Bode diagram, which is spectral response of particular linear system. And like you have a lot of interconnections here to other domains. And again, if you're not familiar with control systems or with other domains that I'm talking about, that's completely fine. This is just one out of million examples that you can think of different connections to different things. But if you're familiar with that, it might kind of ring the bell that it's somehow related to what you know already from previous courses. All right, so spectral radius is defined as rho of A, and this is maximum magnitude, like farthest away eigenvalue from origin. The spectral radius, yes.
You're saying that this S is the poles, which we can see in the something like after Laplace transform.
Yes. So you're making, like in state space systems, are you familiar a little bit with controls?
Yeah, control system.
So in control systems, you will have something like that. You will have representation, dynamic representation of your system. The system will look like right, example of system, okay? So you'll have x dot, function of t, of course, but I can skip the function of t. It's ax plus bu, and then output of the system in time will be cx plus t, but t is typically 0, whatever, okay? You can write plus t. All of them are function of t. These are constant matrices. So this is standard state space representation of any dynamical LTI system. All right. So this is practically a system of differential equations of first order. And solution of the differential equation starting from some initial conditions will give you dynamical states of the system, like how it is changing in time. So solutions f x of t, so each one of them will be vector, okay? Each one of them is vector. So it will be x1, 2, 3, 4, 5. Each one of them is just how the state is changing in time. It's a function of time, and this will be the solution of differential system of differential equations. So what happens is to find g of s, which is Laplace domain. You're doing Laplace transform on this one and on this one, right? So you get practically derivative is multiplication by s in Laplace transform. So it's like s times Laplace transform x of s equals a x of s plus b u s, right? I did just Laplace transform to both sides. And same thing with y. So y of s equals c x of s plus d u of s, right? So I just did Laplace transform on both of these equations in matrix form. Now what I need to find is, by definition, this is y of s divided by u of s. Okay, so this is algebra from now on. And what you will get is C as I minus A inverse B plus D. This is almost what you get from solving that system of equations. Okay, so practically getting rid of the x here, right? Which will be just getting rid of that part. And then you get something like that, because from here you get, think about that as S I x. This is not changing anything, right? Because multiplying by I is not changing the vector. So it will get, I will take that part, move it here, this negative sign. So it will be SIX minus AX. That will be SI minus AX equals BU. Right? So now I want to get rid of that thing to write what X is. So X will be multiplying by Z inverse from both sides. You will get SI minus A inverse. Right? Something like that. And now Y will be equal C times that thing. Plus du. I just substituted that x here in that equation. Okay, so it's C times that thing plus du. Now I can take u out to write it like that. So y divided by u will be that thing. Okay, so this transfer function. So if you pay attention, you have that thing inverse, right? So you will see that this is eigenvalue of that matrix, because you will need that this determinant will need to be equal to 0, and we will see that in a second how it relates to that particular equation. Okay, this is how you compute eigenvalues. You compute determinant of Si minus A to find S. This is polynomial. Okay, determinant is polynomial in that case. And when you will solve it, you will find all of the eigenvalues. And this is why these are practically eigenvalues of that matrix to make that thing work. But these are exactly the poles, because this is denominator of that function. Because when you compute that function, it will be 1 divided by det Si minus A times some other matrix. Okay, so this will be your denominator polynomial. Right? This is how this solution will look like. Inverse matrix. It's always like that. Right? But I'm jumping ahead, I guess, too much. Okay, so here is the geometric intuition behind what eigenvalues are doing. Oops. have it first. Okay, this is geometric intuition on what eigenvalue or geometric mapping is doing to squares and circles. Just if you're thinking about each point on a square as particular vector in space, or particular point on a circle as particular vector. So how each point is mapped kind of out by multiplying by matrix A. So here's what happens. And here is a visualization of how eigenvalues might appear. So let's say square by a particular matrix might be mapped into that kind of parallelogram, all right? And circle will be always mapped into some sort of ellipsoid. So when you're looking on that ellipsoid, how different points mapped, you will have multiple different options here. So one option will be that you have some points moving outside, so they are not continuation of the line connecting them to the origin, but some points might be continuation of the origin, and this will be eigenvectors, obviously. And you might have two of them, like in that case, okay? You have one looks that way, another looks that way. They are always orthogonal, okay? So eigenvectors will be always orthogonal, which is a very nice property for us. And you might have two of them, okay? This will be very nice basis for presentation, but they don't have to be orthogonal like that. They could be like that, okay? So you still have two eigenvalues, but they are tilted at a particular angle to each other. All right, so this is another kind of mapping. Sometimes they overlap, and then you have only one direction, which is not changing the direction, okay? When you're mapping that circle to the ellipsoid by multiplication by a matrix. And sometimes you don't have any, like all the directions are changing. Okay, so these are the options. So you can have 0, 1, or 2 eigenvectors for your 2x2 matrix. It could be all kind. And this is kind of geometric intuition, how it might look like when you're mapping different things. Right? Any questions on that? Yes.
So the number of eigenvectors is the rank of the matrix.
Up to n. It cannot be larger than n, but it can be smaller than n.
It's not determined by the rank.
No. So multiplicity of eigenvalues, you can compute multiplicity geometrically of eigenvalues. So it's when determinant of Si minus A will have multiplicity of roots, this is where we have multiplicity of eigenvalues. So you can compute it. It's like, for example, if we'll get to characteristic polynomials, but when characteristic polynomial has, let's say, S squared times some other stuff. Okay, so you have two of the poles at 0. You have multiplicity. In that multiplicity, you might have same eigenvector or two different eigenvectors corresponding to that. It's called geometric multiplicity. This was the name I'm trying to translate from. I think it's called geometric multiplicity of eigenvectors where single eigenvalue corresponds to two different types of eigenvectors. Something like that. So and again, you have infinite number of eigenvectors here. You have all kind of tricky situations here, okay, with multiplicity. When you have separate eigenvalues which are all different, then you have n eigenvectors. This is the simplest one. Like when all of them are different, all of the eigenvectors are different. But when they are the same, it could be all kind of. Okay, so these are those kind of extreme cases where they are behaving weird. Most cases will be like case 1 or case 2. Relatively simple case. Okay, so let's see how we solve that. This is derivation of computation of eigenvalues. So why this formula on the board actually works in general. And here's how you go. So you need to solve that equation of ax equals s times x, and to find eigenvectors x and eigenvalues s. As I said, I'm using that trick that multiplying by I is not changing the vector because I will need to subtract that thing from the left side, and I will move it to the left side, which is exactly the same thing as Sx, right? And then it needs to be a vector of zeros. And you have all of the dimensions here to match. All the dimensions obviously need to match. So I can write that thing as A minus Si equals to 0. That kind of equation, okay? So that equation obviously has trivial solution when x equals to 0, but we don't care about that part. We don't care about eigenvector 0. It's not even vector really. I mean, it is vector, but trivial vector. Okay, we are not interested in direction 0. It has no direction. We are interested in non-trivial solutions of that equation. And this is, pay attention, this is a system of linear equations. So when the system has non-trivial solution, then this matrix is not invertible. Because if it is invertible, if A minus Si is invertible, then the only possible solution is x equals to 0. That's it. You have no other solutions. So we are looking for the case where A minus Si is not invertible, singular. All right? And if you remember theorem about determinants, which is saying when matrix is invertible when determinant is not equal to 0. Which means it's not invertible when determinant is not equal to 0. So our condition will be for finding non-trivial eigenvectors and eigenvalues that the determinant of that thing equals to 0. But pay attention, what is that thing? S is variable, right? A is just a bunch of numbers in table, and I is a bunch of numbers in a table. When you're doing determinant of that thing, you will have some sort of polynomial in terms of S, of order n typically, right? So you need to find the roots of that polynomial that will be equal to 0, and this will be your eigenvalues. So this is how you compute your eigenvalues. You just compute that determinant, you will get some polynomial like that with some coefficients, and pay attention, these are not coefficients of matrix A, these are just alpha, whatever. These are different, just numbers, okay? Just coefficients of that polynomial, whatever they are, all right? And polynomial of order n, or degree n, has always n complex roots. This n complex roots will be your n complex eigenvalues, okay? So all of the solutions of that polynomial equals to 0 will be your eigenvalues. That's how you compute them. All right. Now, given that you have that eigenvalue, for each eigenvalue, you can put it back into that system of equations. Now it will become particular number, whatever it is. Could be complex number, but still number. And you just solve the system of equations to find x. And you will have always infinite number of solutions. You have to, because you have infinite number of eigenvectors corresponding to that particular eigenvalue. So if you don't get infinite number of solutions, you did something wrong in your computations, right? It has to have infinite number of solutions. Well, this is how you compute your eigenvectors. You just solve the system of equations for each S. So you're putting Si here and solving the system, putting another Si here, getting another solution, and that's it. That's how you do them by hand, which is not very convenient, long process. And additional definition that I want to define is characteristic polynomial. So characteristic polynomial is the determinant of Si minus A. This is a polynomial, roots of which will be your eigenvalues. And we will solve that equation, find all of the roots. Okay, so here's an example. Again, I'm writing that formula for you to not to remember. These are two things that we need to solve to find it. Let's say you have that matrix of 1, 2, 0, 3. So determinant of Si minus A or A minus Si, which is practically the same thing in that case. So this is Si. It's 1, 1 matrix, which is identity matrix. It will be S and S here when you doing that, right? When you multiply by scalar S. So it's 1 minus S, 2 minus 0, 0 minus 0, and 3 minus S. So this is a determinant that you need to compute. So it's 1 minus S times 3 minus S minus 2 times 0. That will be that thing. Okay? So this polynomial equal to 0 will have two roots. And these two roots will be obviously 1 to solve that first part. And second root will be 3. So those are eigenvalues, 1 and 3. Right? Solutions of that quadratic equation. that clear why this is the solution of that equation? It's already in factored form. So each factor of need, like each one of them might be 0. If you multiply 0 by whatever, it still will be 0. So if you're replacing s with 1 here, it will be, first one will be 0. If you're replacing s with 3, second one will be 0. So these are the roots, and you have only 2 of them. In that case, both of them are real. Sometimes you might get them complex, depends on solution of quadratic equation, obviously. So for that first eigenvalue, which is 1, I'm substituting v1 and v2 eigenvector and that eigenvalue here, solving that system of equations. Ax equals sx. In that case, x equals v1, v2. Right? So solving that system of equations, getting some solution which is v2 equals 0 and v1 equals 2v1. Obviously, the system of equations has infinite number of solutions because I can choose v1 whatever I want. So I would choose it 1. Again, to have norm 1 or to have maximum 1. In that case, it's the same thing. And I will choose vector which is 1, 0. I could choose like 5, 0 or 5 million 0 or whatever. Okay, any number here and 0 here, because solution need to be v2 equals to 0, v1 equals to itself, which is like whatever. Right? So this is first eigenvector. Same thing with 3 here. Second eigenvalue is 3. Solving the system of equations, I get v1 equals to v2. This is condition from the first equation. And from the second equation, v2 equals to v2, which means no information. So solution of that, again, infinite number of solutions. v2, you choose whatever you want, but v1 needs to be equal to it. So both elements should be exactly the same element. So you can choose 1, 1, or 1 divided by square root of 2 to make norm 1 in each one of these elements, okay? So it just needs to be same element here and there. These are eigenvectors. Any questions on that? Yes.
So as far as you have your eigenvalues to be some scalar, for some cases, the eigenvectors, the exact number of the element does not matter if it is just maybe a scalar multiplication of the vector. Does not really matter.
It could be any scalar multiplication of the vector, yes. But pay attention that in 2x2 systems, it's relatively simple because you can have only one of them as free variable, another one computed from that free variable, whatever it is. But if you have like 5x5 system, you might have 2 free variables or 1 free variable or 3 free variables. Depends on that, you will have different number of eigenvectors, which are spanning that entire subspace of solutions, right? This is why sometimes you have different multiplicity of these vectors. And sometimes you have diagonalizable matrices, sometimes you don't have diagonalizable matrices because of that multiplicity. And for 2x2, it's simple. For higher dimensions, it's a little bit more complicated. But the idea will be exactly the same. You just need to solve the system of equations and to identify how many free variables you have. And then choose these 3 variables, whatever they are, and compute the rest. You will have your eigenvector. Right? Any other questions? Okay, another interesting practical example, last for today. Eigenvalues of that specific matrix, which I will call R. This is not the same R as we discussed before in QR and that kind of stuff. But this is called rotation matrix. This is why R. Rotation matrix is used a lot in computer vision and graphics and multiple other domains. It rotates vector by angle theta. And theta is parameter, whatever number. All right. So if you multiply vector by that matrix, it will not change its size, but it will rotate it by angle theta, counterclockwise. All right. This is what it does to any kind of vector. So let's see what are the eigenvalues of that type of matrix, which is kind of interesting by itself. So let's compute it. So the determinant of R minus SI, it will have that kind of determinant. So you multiply that part by that part minus that part times that part, and you get cosine theta minus S squared plus sine squared theta. Now I will open the parentheses here. So it will be cosine squared minus twice cosine times s plus s squared plus sine squared. But cosine squared plus sine squared is 1, trigonometry, okay? It's 1 minus 2s cosine plus s squared. It's quadratic polynomial, practically speaking, and cosine theta is some number, depends on theta. So let's compute roots of that polynomial, which are eigenvalues of that kind of matrix. This will be the roots. So pay attention that 4 cosine squared theta minus 1 will be just twice sine of theta. Why? Because this is like same formula. Sine square plus cosine square is 1. So cosine square minus 1 will be sine square. And square root of that will be minus sine square, okay? Because it's like inverse. So it's imaginary j, practically j times sine theta. Okay, this will be the solution. This is, you have two roots, obviously. Both of them are eigenvalues of that particular matrix, complex eigenvalues. Now you know Euler theorem, and Euler theorem means that cosine theta plus j sine theta is exponent of j theta. Okay, remember that theorem? Pretty famous. So you can write the same thing as e to the plus minus j theta. This is the set of eigenvalues. But what that thing is? Like if you multiply by that eigenvalue, what happens? Practically you add angle theta to whatever vector you have. If you, this is scalar, right? It depends on theta. If you multiply by e to the j theta, what happens is you just rotate it by angle theta, that vector. Because in polar coordinates, multiplying by exponent of j theta is just multiplying by absolute value of it. And absolute value of exponent will be 1, right? Always for any theta. And angle of that thing, you add in that angle to the vector, and angle will be theta. It's defined that way. Okay, so multiplication by exponent to the j theta practically rotates the vector by angle theta. Positively or negatively, depends on the sign of the j. All right. So this is exactly what we're expecting from rotation matrix to do. This explains what matrix does to vectors in general. All right. Any questions?
So about the eigenvalues and then the eigenvectors. So if the eigenvectors, they are the directions which do not change, and then the eigenvalues tell you how to scale those directions. Then the eigenvalue must have some standard units that will kind of guide you whether you are scaling the direction 3 units, where 1 unit is this or that, because it is kind of...
Sure, I mean, you can compute the same thing in units, but this is unitless because we're using just numbers. So units are same in each direction, and all the numbers in different directions will have the same units. Whatever they are, depends on your problem. In practical problems, obviously, you will have units, yes, for all of these dimensions. Each value in the matrix A will have particular, you can think about data in radian, right? It's unit, but it's just number, right? So when you multiply by exponent of whatever j theta, you just rotating that by that angle theta, your whatever vector you choose. What happens is that none of these vectors in that case will rotate to the same place except theta equals to 0, right? So it's like you're not rotating by any angle, 0 to pi. This is the only case, and 180. This is the second case, it will kind of flip it to the opposite direction. So these are the only directions which will not change the actual direction, right? But what we achieved here is we replaced multiplication by that, I don't want to call that complicated matrix, it's simple matrix, but still multiplication of vector by a matrix. Instead, we can replace it with multiplication by scalar, which is the eigenvalue. And it also gives you understanding of what it does. Right? So this is giving you much better understanding of what is happening. All right. Good morning, everyone. How are you? Hi. Good. Any questions on the previous lectures? I published new homework and also graded previous ones. Not really graded, just gave everyone good grade. Hopefully you're happy about your grade right now. As I said before, the point of this course is not to really evaluate your deep knowledge in linear algebra. It's more about numerical methods, what you learn about programming different things, understanding of different principles, and giving you overview of other things. And today I plan to use new technology, so bear with me. As you may notice, this board is not great for writing different derivations and stuff like that. Too tiny, and I need kind of to put stuff on the board in a complicated way, not very consistent way. So I'm planning now to draw maybe on the tablet instead of that, so it will be much more convenient in that sense, hopefully. So we'll see how it goes. Okay, so previous time we discussed eigenvalues. We started to discuss eigenvalues, and I gave theoretical introduction what eigenvalues are, how you compute them by hand. Nobody obviously computes eigenvalues by hand, but practically speaking, we went through motivation why we need eigenvalues and eigenvectors. So these are the kind of vectors which are not changing their direction when you multiply by matrix A. Which means eigenvectors of matrix A are not changing their direction. They can flip to the opposite direction, but not changing angle to anything but 0 or 180 degrees. Okay, so these are the only possibilities for eigenvectors. Now, we also learned a few more things. So we computed these eigenvalues, how to compute them in MATLAB. We learned about geometric intuition behind what they are, how they map circles or squares in space, in two-dimensional space at least. And then we learned how to compute them. And this is practically by computing determinant of Si minus A or A minus Si equals to 0. And you get polynomial, you find roots of that polynomial. And then these roots are eigenvalues. And then you solve a system of linear equations and you get eigenvectors, which is again good for small systems like 3 by 3, 4 by 4 maybe. But if you go into higher order matrices like 100 by 100 or 1 million by 1 million, sometimes you have much bigger matrices even, then it's not feasible because computing determinant is too difficult. It's too complicated computationally. So we went through the characteristic polynomial, a few examples. And then we complete our previous lecture with that kind of example where we took rotation matrix, which is used a lot in computer vision, and this matrix is practically rotating any kind of two-dimensional vector or two-dimensional point in space and giving it different angle, depends on angle theta. So if you multiply any vector by that particular matrix R, you rotate it by angle theta, and we showed that this is exactly what eigenvalues show you. And there was also a question like, what do we do with the eigenvectors of that thing? So what are the eigenvectors of that kind of matrix? Which is interesting because here you have only complex eigenvalues, right? So you don't have any real eigenvalues. So all of them, unless theta equals to 0 or pi, these eigenvalues are complex, and eigenvalues, like everything is complex here. But matrix is real, but everything else is complex numbers. So I want to show you how to get to actual eigenvectors of that matrix and what they will be, which is a little bit interesting and kind of educational, that you can get multiple different types of eigenvectors and how they might look like. Sine theta and sine theta, sine theta, sine theta. Oh, can you see that on the screen? And you have eigenvalues which is S1, 2 equals exponent plus minus d theta. Okay. All right, so we need to find vectors. So eigenvectors will be same matrix, cosine, sine, let's keep theta because it's like all the cosine and sine will have theta in them. So I will just write all the regular values. We'll have sine, cosine, sine, sine, and somehow paper times that vector, which is 1, 2. This is equals e to the plus j theta times same vector v1, v2. All right, so far this is how I compute eigenvectors. So for that same, change color to 10. Okay, we'll figure it out later. All right, so I'm solving system of equations. So system of equations will be, first line will be cosine times v1 minus sine times v2 equals exponent j theta times v1. Second line will be sine times v1 plus sine times v1 v2 equals exponent j theta times v2. Right. Now we need to solve that system of equations. So this will be, so exponent of j theta is Euler theorem. So you can write that as cosine times v1 plus j sine times v1. Okay, and this one is similarly cosine v2 plus j sine times v2. Okay, so now things are canceling out. So cosine v1 cancels with cosine v1. Here you have cosine v2 cancels with cosine v2. So you have new system of equations. And this new system will be that minus sine times v2 equals j sine v1 times v1. Okay, so again, sine is cancelled with sine. This one you get minus v2 equals j v1. Right? From the second one, you get, you can cancel the sine here and there, and then you get v1 equals j. Get it right? v1 equals j v2. Like that. Okay. Something is wrong with my first one. Minus. It's incorrect here. Just a second. 1 cancels 1. You get minus v2. 2 equals 1. Equals j v1. That's correct. v1 equals j v2. That's correct. Okay. So from this two, you get new system of equations. If you multiply by j on both sides in the first equation, you get v1 equals j v2. And then from the second one, same thing. v2 equals 2v2. The same thing, right? We're used to write on the board. Tablet, first time I'm using tablet actually with pen. Difficult to follow. V2, let me see, what do we get here? V1 equals V2. If I multiply here, we get plus J times V2 V1. So this is correct. Second one is V1 equals J V2, right? From here we get vector V1. So what do we choose as a vector? So both equations are the same, right? So you need to pick one variable, which is just some constant, whatever it is. And second one, you can pick based on that equation. Okay, so the equation will be that second one is J times the first one. Right?
What
Yes.
happened to that negative sign?
Hmm?
The negative sign.
So minus V, so you had something like minus V2 equals negative J V1, right?
Is it negative V2 or positive? One of them was positive, the other one was negative.
So it was minus V2 equals J V1. Okay. This is, so you can multiply by minus both sides, right? So you'll get plus here and minus there, right? And you can multiply also by J both sides. So you'll get J times V2 equals minus J times J V1. But J squared is minus 1, so it's like this one is 1. So V1 equals J V2. Okay? So it's the same equation. So let's pick one of the possibilities, J and 1, for example. We pick like 1, and second one will be J multiplied by the by that thing. All right. So second one goes like that, very similarly. So you have cosine minus sine, sine, cosine, times V1, V2, exponent of minus J theta, V1, V2. A different eigenvalue, all right? So you get that same system of equations, and you get cosine times V1 minus sine V1 V2 dot equals exponent minus J theta times V1. And then you have sine V1 minus plus cosine times V2 equals same exponent and again this equals to cosine of minus theta will be same cosine, so it's still cosine of theta times V1 plus J sine, but in that case it will be J sine of minus theta, right? So sine of minus theta is minus sine theta. So it will be practically minus here, sine times V1. All right, second one will be sine cosine first, cosine times V2. And then again, minus J sine times V2. All right, here things are again canceling. To get sine is cancelled with cosine. Then this is cancelled. Cosine is cancelled with cosine. And again, you have system of equations. And that system of equations will be minus V2 equals minus J1. V1 equals minus J V2. So from here, you solve it and you get second vector 1G. Okay. So these are eigenvectors of that thing. You have also other options. You can choose other vectors like 1 minus j and 1j, for example. They also will be fine for that kind of system. All right, so you have multiple different ways to do that, and it's multiplication by a constant. And this constant could be also complex constant in that case, because everything is complex here. So all of them are eigenvectors, all right? So here's interesting property of this particular eigenvector. So if you're looking on this eigenvectors, try to do dot product between them and see what happens. Can you do dot product between these two eigenvectors? No. Well, what do you get?
Orthogonal, so 0. 0?
So if they are orthogonal, you get 0. If they are not orthogonal, they are not 0. Should they be orthogonal?
Barely, no.
Not necessarily. So not necessarily all eigenvalues are in particular giving you dot product 0. So I can tell you condition for matrices to produce orthogonal eigenvalues, which are very convenient for our basis, if you remember, right? So having orthogonal vectors for basis is very convenient. So these matrices are also called normal matrices, all right? And normal matrices have very nice and convenient properties that you can check. This property is like that. So you get, if matrix A transpose times, say, matrix A equals AA transpose, then they are normal and their vectors will be orthogonal to each other, pairwise, all of the pairs, which is very convenient property, okay? So you can check that property and see if matrix is corresponding to that, and then you get orthogonal vectors. This is relatively easy to check, right? Nothing to invert, nothing to like log computations, it's just multiplication and addition type of operations. So this is called normal, and the geometric intuition behind that type of matrices is that this matrices, when you multiply vector by vector, the type of matrix, it's rotating and reflecting and scaling the space, but not squeezing it in particular dimension, okay? So the scaling happens to all dimensions equally. So if you squeeze or stretch the space, it happens in every single dimension similarly, okay? You're not squeezing one dimension more than others or stretching more than others. So these normal matrices, which are pretty popular in multiple different applications, okay? They have the properties that they just rotate the space, they scale it equally to all dimensions, or they flip it in some way, but they are not squeezing it, not squishing it in a way, all right? So this is that kind of matrices. They are not doing that to vectors differently in different dimensions. They work similarly in all dimensions. So these are matrices of that kind, okay? And this matrix is clearly doing rotation, so it's not really doing anything to the vectors. So it's nice matrix in a way, okay, for any data. Any questions? Okay. Okay, now we have some properties of eigenvalues, which are very important properties that we'll be using in multiple different domains, especially control systems and machine learning and other topics. So first property is a trace of matrix A, which is, if you remember, it's sum of all the diagonal values. Like you're taking all of the main diagonal, adding all of these values together, this is trace of the matrix. It will be sum of all of the eigenvalues. So why is that the case? I'm jumping a little bit forward, but this is the explanation. If you learned linear algebra, you will understand what I'm talking about. If you never learned linear algebra, you can skip my explanation, okay? So what happens is, let's take a very simple case where matrix is diagonalizable, which means there is similarity transform, which can convert that matrix to diagonal matrix with particular transform T inverse times diagonal matrix times T. Okay, so you'll have some invertible matrix, which is converting that matrix into diagonal. And obviously diagonal values will be eigenvalues of that matrix. Now, property of trace is not changed for similar matrices, which are going through that type of transform of T inverse times matrix times T for any T, okay? So this is not changing eigenvalues. And since diagonal matrix has all of the eigenvalues on the main diagonal, obviously you will have same trace for both matrices, okay? Which means that diagonal matrix will be just sum of eigenvalues on the main diagonal, and your original matrix has exactly the same trace, so this trace will be also sum of all of these eigenvalues, okay? This is the overall idea of the proof, how you know that this is true. Now you have similar property for multiplication or product of the eigenvalues. So product of the eigenvalues is determinant of the matrix. And again, if matrix is diagonalizable, then after similarity transform, you can prove that determinant is same practically to that matrix as after similarity transform. And then you just multiply all of the eigenvalues on the main diagonal, and you'll get exactly the same result, determinant of the original matrix. Now, here is a trick. When it is not diagonalizable, you can always write it as Jordan form. And again, I don't know if you even learned about Jordan form, but Jordan form is sometimes you have not diagonal values, but you have ones above the main diagonal. This kind of blocks of main diagonal numbers, and then ones on the secondary upper diagonal. This is Jordan form. So any matrix could be written with similarity transform in Jordan form, which is a little bit more sophisticated than just simple diagonalization. But for these matrices, again, trace is the same trace because you have eigenvalues on the main diagonal, and those ones on non-main diagonal will not change the trace, okay? And also determinant of that matrix is same determinant. So you're just multiplying all of the values on the main diagonal, and you don't care about these ones above the main diagonal because they are not participating. It's like multiplied by 0. Like if you have triangular matrices, this multiplied by cross 0 here. So it will disappear that one, all right, that block of ones. So again, you get same kind of value, but you have much deeper connection here. And each time I'm describing that, I'm getting to middle school, and people didn't learn it in middle school for some reason, whatever that reason is. And so my analogies to different things make no sense to people because what I learned in middle school or high school is completely different from what you learned in middle school and high school in terms of like basic algebra, okay? Have you heard about Vieta's formulas? Vieta theorem formula. So this is the case where like it's all interconnected through basic algebra, but since you don't know the actual theorem, I'm kind of connecting it to air because you don't have that background. Okay, so basically this formula says something like that. It has relations between roots of polynomials to its coefficients. Okay, this is the theorem. It connects how roots connect to actual polynomial coefficients. So you have polynomial of nth order, whatever. So second coefficient of that monomial, or when the first coefficient is 1, like s to the power of n plus first coefficient times s to the n minus 1 and so on. So that second coefficient is always minus sum of all of the roots. This is one of the formulas, Vieta's formulas, okay? Like negative sum of all of the roots will give you second coefficient. Last free coefficient of the polynomial is always multiplication of all of the roots, no matter what polynomial you take. Like if you multiply all of the roots of the polynomial, you'll get plus free coefficient. Okay, and proof is relatively simple. You're just taking factorization of polynomial as, let's say, s minus s1 times s minus s2, s minus s3. So just putting like s equals to 0, and you get multiplication of all the coefficients which are the roots, right? Like s1, s2, s3, s4. You just multiply them, and you get that number, right? Because this is what comes from factorization. But you have similar formulas for all of the other coefficients. It's all of the pairwise combination, triple-wise combination, and added together, all of them. So that's very similar to computational determinants, actually, how you compute determinants, because determinant gets you all kind of like determinant 3 by 3 is all combinations of 3 numbers that you have in determinant. You have all kind of connections here. But what I want to connect it to is something else. So first of all, the property that A minus Si times identity matrix is singular almost by definition, because determinant of Si minus A or A minus Si should be 0, and then this matrix will not be invertible, so it's singular. But this is the important property, which probably used in modern control every second line of computations that you do, okay? So instead of doing determinant of Si minus A, you can write that polynomial, characteristic polynomial of second order matrix practically immediately using Vieta formulas. These are the formulas. Practically second coefficient is minus trace, because we proved that this is sum of the minus sum of the roots of that polynomial. And free coefficient is just determinant of matrix A, which is very easy to compute because this is product of all of the eigenvalues of matrix A. Okay, so this characteristic polynomial of matrix A is just minus trace as a second coefficient and determinant as a third coefficient. Right? This is very easy to use formula, very easy to remember. Okay, another property, S equals to 0 at eigenvalue of matrix A only if and only if A is singular. And this is also obvious from the third property here, because if Si equals to 0, you get just A singular. It's practically a particular case of that type of equation. Any questions so far? Okay, so now we have geometric intuition behind how you compute with eigenvalues, because it will be important to understand geometrically what it means to write something in system of coordinates which are eigenvectors now. So eigenvectors, as you know now, it's like scaled and rotated space from your original coordinates of your matrix A. When you're doing diagonalization of the matrix, it kind of rotates the entire system and makes it some other angle. And here you have those black lines describes that kind of system of coordinates, which is a new system of coordinates compared to the original rectangular system of coordinates, which was there before based on the matrix A. So we want to compute practically multiplication of matrix A, which is regular given matrix, by vector X. So vector X is given by the green line here, and then vectors V1 and V2 are eigenvectors of that matrix A. So we want, obviously we can just multiply, okay, as we usually do, but we want to do that through eigenvectors and eigenvalues. And the idea is that since eigenvector is something which replaces multiplication by matrix by multiplication by a scalar, this is how we want to compute it. Just number times V1 plus another number times V2. This is the overall idea. But what are these numbers? All right. So here's how geometrically it works for matrices 2 by 2, because obviously higher dimensions more difficult to imagine, but I will explain geometry in 2 dimensions first. So here's how it works. So first of all, if you're looking on vector X, and again, you have vector V1 and V2, which are hopefully orthogonal. For that case, it's for normal matrices, okay? So what happens is you are finding projection of that vector X into each one of these X's. Now, we will call that projection modulo alpha, which means the size of the projection will be alpha 1, and on that side it will be alpha 2. And that vector, which has that length, we will call it alpha 1 times V hat 1, which is like unit vector in that direction. And this will be alpha 2 times V2 hat, which is unit vector into that direction, into orthogonal directions, okay? And this is what you have in that picture here. So you can see that direction is alpha 1, V1, and that direction is alpha 2. And the idea is that these are just projections. If you remember, projection into that vector would be dot product between the vectors divided by norm of the vector. Remember that part? How you project one vector into another vector? So you have these formulas here also, how you compute alpha 1 and alpha 2. You just doing dot product between V1 and your vector, divided by norm of V1. So it will be just regular dot product if it is already normalized. Which means if I replace v1 with v1 hat, it will be just v1 hat dot product with x. And second one will be v2 hat dot product with x. These are the projections, okay, or sizes of the projections actually. This is a scalar size of that vector. All right, so far? So these are just projections. What what eigenvalues do, they stretch the space by that eigenvalue number, whatever that number is. Which means if you have eigenvalue of 2, it just stretches that vector by 2 in that direction. Okay, so each direction has its own stretch or squeezing of some kind. So your final result will be in that direction, it will be stretched by S1, and in that direction, it will be stretched by S2, whatever these numbers are. So the final length of each one of these components, the coordinates of that new vector after multiplication by A, will be S1 times alpha 1, and this size will be, this one will be S2 by alpha 2, and this will be S1 by alpha 1. Okay, so this will be like total length. And this is what that formula at the bottom here says that you have here, right? That formula. So it says that multiplication by matrix means you take projections to this axis of V1 and V2, stretch them by S1 and S2, add them together, and you will get vector AX. Okay, some of these two vectors will be the red vector here. So this vector will be some of these two projected and scaled vectors. Okay, so this is how it will work. Let's say you use unity vectors, and then here's example how you can do that. Right? Let's see. Here. U1. All right. You have matrix which is A, is 1/2 of 5, 1, 1, 5, and you want to multiply it by vector x is 2 and 4, and I will not compute eigenvalues and eigenvectors, I will just give them to you. So S1, 2, these are eigenvalues, will be 2 and 3, and eigenvectors will be V1 plus 1 divided by square root of 2, 1 divided by square root of 2, and then V2 will be vector which is 1 divided by square root of 2, 1 divided by square root of 2. Okay, these are two eigenvectors, and I already normalize them to make them orthogonal and normal. Right. For simplicity, that I will do only dot product instead of dividing by norm each time. But you can go through the full formula if you want it. And you can check that A transpose A equals AA transpose, and then V1 is orthogonal to G. You can directly check that on that particular matrix. All right, so eigenvectors will be orthogonal here. Now, given that this is true, here's how I compute alpha 1. So alpha 1 is projection V1 dot product with 2, 4 is my vector x. Okay, this is a projection. This V is normalized already. So it will be dot product between the minus 1 divided square root of 2, 1 divided by square root of 2, dot product 2, 4. So if you compute that, you get 2 divided by square root of 2. Okay. That's what you get. So for alpha 2, you're doing the same thing. So it's V2 dot product with 2, 4. And what you'll get is 6 divided by square root of 2. And now you can compute A times X. So AX will be S1, alpha 1, V1, plus S2, alpha 2, V2. That will be 2 times 2 divided by square root of 2 minus 1 divided by square root of 2, 1 divided by square root of 2 plus 3 times 6 divided by square root of 2. Complicated, but just technical. Eventually you'll get 7 and 11. All right. And if you multiply obviously matrix A by that vector directly, you get the same result. Any questions on that? So this is kind of geometric intuition that you projected, and we will need that intuition when we will get to numerical methods, how to actually compute these eigenvalues. Yes.
So in two-dimensional sense, where we are kind of seeing, we are taking the eigenvector to be like 1D.
Yes.
I understand that when you multiply by the eigenvalue, you are just stretching it. So what if the eigenvector is in 2D, something like a sine wave? If you are
stretching in each one of these dimensions, you can stretch it in multi-dimensional space. You think about that a system of coordinates which you modify, which you scale in each dimension separately. So when you're doing that in regular system of coordinates, you cannot really do that because each dimension will be dependent on other dimensions. They will be kind of cross-connected. But in eigenspace, you can do all of them separately. This is the thing, that each dimension scales completely separately because they are eigenvalues and eigenvectors. This is the convenience of that particular space, and this is why we typically diagonalizing matrix first. Then we work in the diagonal eigenspace, and then we get back to the original space of the matrix A, or column space of matrix A, which is kind of complicated procedure, but it's not as complicated when you see how easy it is to manipulate diagonal matrices. We will see that in a second, like why diagonal matrices are so nice and why we want them to be all diagonal. It's almost like working with scalars when you work with diagonal matrices. Any other questions? Okay, so similarity transforms. As I mentioned already today, if you learned it, you learned it. If you haven't learned it, just believe me that they have all kinds of nice properties, very nice properties. And matrices A and B are called similar if there exists such matrix T, invertible matrix T, that A equals T inverse times B times T. Okay, this is that kind of similarity transform. And their nice properties is that they have same eigenvalues, they have same trace, they have all kinds of nice properties. All these nice matrices, okay? And if you think about the intuition behind what this transform is doing, it's practically transforming coordinates of the matrix A into matrix B. So if you had if you thought about columns of A as coordinates, a particular space, okay? Now you can think about matrix B as that new system of coordinates, and this matrix T is transforming from one to another, and you have that kind of interesting loop where T and T inverse will go to B, and then from B it will go back to A. So each multiplication by T is practically transforming system of coordinates of your given matrix. That's how you can think about that. Now, there's also change of basis. And again, we talked about basis as system of coordinates in a sense. And you just mapping the system of coordinates back and forth using this T transform. As I mentioned, you have similar eigenvalues, and here is why. So if you start with determinant of like what we want to prove here, this is actually derivation of why they have the same eigenvalues, matrices A and B. So what you actually want to show is that determinant of A minus SA equals determinant of B minus SI. Sorry, A minus SI equals determinant of B minus SI, which means if they have the same characteristic polynomial, they obviously have the same roots. And if they have the same roots, they have the same eigenvalues. by definition, okay? So that's what I'm developing here. So what I'm doing here is determinant A minus SI equals practically, this is trick to convert here, but first step is very simple. I'm just replacing A with my definition of A using B, which is T inverse B T, which was defined here, right? So that definition. So I'm taking that definition, writing that definition here instead of A. And now I can do some trick with that thing. Since this is S times identity matrix, this is practically, you can multiply it by any matrix and you will get that matrix times S. All right, so if you multiply by T or T inverse or whatever, it will just become that same thing times S. So if I multiply by T inverse and T, left and right, what will happen? So it will be S times T inverse T. But T inverse T is I, so it's like nothing, okay? So you get back to I, so it's still SI. So I can multiply by T from the left and T from the right without changing anything because they cancel out, right? So that thing is still SI by multiplying by T inverse and T, okay? But now I can take that T inverse and that T inverse out of the parentheses, distributivity law, okay, of matrices. I'm taking it to the left from the parentheses, and I'm taking T to the right from the parentheses, okay? And making something in the middle, which will be T inverse times B minus SI times T, like that, okay? And this is the same thing. So if you're opening this parenthesis, you'll get back the original form. But determinant of multiplication is multiplication of determinants. All right, we saw that rule some time ago. So you can take it as determinant of T inverse times determinant of SI minus B or B minus SI times determinant of T. And determinant of T inverse is 1 divided by determinant of T. So they cancel out these two. And you get what you wanted, which is they have exactly the same characteristic polynomial, which means that everything works out. They have exactly the same eigenvalues. Any questions on that? This is tricky but relatively simple derivation of that rule. Another rule is that A is similar to A transpose. You can always find such a transform for any square matrices A. You can find similarity transform, which transforms it in just transpose of the same matrix. And again, A and A transpose have the same eigenvalues, which is very convenient for us. It will be very important for us as well. And if T consists of linearly independent eigenvectors of B, then A is diagonal. And this is practically a basis for diagonalization of any matrices. And we will see how you do that. This is how you do that. So this is just procedure. I'm not explaining why that works. This is just procedural thing. How you compute diagonal matrix out of regular matrix, how you diagonalize matrix, if it is possible. So if it is possible, and not always it is possible, but in many cases it is possible to diagonalize matrix and to write it as A equals T times some diagonal matrix times T inverse. This is how you do that, okay? So the procedure is very simple, saying find all of the eigenvalues of the matrix A, put them on the main diagonal of matrix D. This will be your matrix D, okay? Second matrix will be just columns of eigenvectors. So matrix T will be just eigenvectors of your matrix A. That's it. This is diagonalization. So if you use that matrix and its inverse of eigenvectors as columns of that matrix, you will get diagonal matrix and diagonal representation for matrix A. And you can also go backwards with that and from diagonal matrix to get A back by multiplying from the left by T inverse and from the right by T. That's it. This is how you go back and forth in these things. Okay, so this is a derivation, and you can see some example here. So the example gives you some matrix that we computed eigenvalues before, and this eigenvalues will be 1 and 3. Eigenvectors will be 0, 1, and 1, 1. So you'll get diagonal matrix with all of these eigenvalues on the main diagonal here. Okay, so these are the eigenvalues from here. And these columns will be practically the things. And you can normalize them if you want to, but you don't have to. They still will be orthogonal if matrix is normal, but do not have to be orthogonal. And in that case, they are not, as you can see, right? So dot product between 1, 0 and 1, 1 is not 0. So they are not orthogonal vectors. And this matrix is not normal in that sense. Now you can compute T inverse, you get that kind of matrix, and you can do all these manipulations to get the diagonal matrix just by T inverse times A times T. And if you want MATLAB code which will produce the same thing, here you have very basic MATLAB code just to check that everything works. The T times T times T inverse will give you the original matrix. All right? Any questions on that? And again, I will not ask you to do diagonalization by hand or anything like that. It's just, you need to be aware that it's possible, okay? That you can convert most matrices into diagonal matrices by similarity transform, all right? So why is it important? This is the key question. Why we care to convert everything into diagonal form? And the reason is that most of the functions that we are interested in have some sort of polynomial taste to it, some sort of powers of matrix A. And computing powers of matrix A is kind of computationally very expensive because you need to multiply, for example, you want 100th power of 100 by 100 matrix. So you need to multiply this matrices 100 times between them, like you multiply it by A, by A, by A, by A 100 times, and each one will be like n squared numbers in it, added and multiplied, right? So it's like tons of computations, a lot of computations. So what happens is we want to use that a lot in representing also other functions like Taylor series. So you know that exponent could be represented as sum of like a polynomial in Taylor series, or sine could be represented partially in particular intervals, or any function could be represented as polynomial approximated by polynomial in particular intervals, okay, of higher and higher order. So this is Taylor series, that's what it is. You're approximating things with polynomials. Now, you can do the same thing with matrices. So if you want to approximate that with matrices, you'll have all kinds of powers of matrix A, and you want higher and higher powers to get better and better approximation, okay? So when you get to all these numerical methods, you will need to compute things of that kind, probably with much higher powers, but this is just one example, where you want some powers of A, which is A times A times A, plus 6 times A times A, plus 35 times I, things of that kind. This will be the kind of series that you want to compute. And this is complicated. But here how we actually solve it. So we decompose A into the diagonal form by finding that transform T, which is just columns of eigenvectors. And then we get the D with eigenvalues in it. But then here's what happens. Let's say we want to compute that particular example, right? So it's something cubed, which means you need 3 times the same thing to repeat that thing. And this is how it will look like. Pretty long. But pay attention to what happens in the middle to all of the T and T inverse. When you write that explicitly, they all cancel out because last T inverse multiplies T, and then another T inverse multiplies T, and so on. They all cancel out. What you have in the middle is practically D to the power of K instead of multiplying all these triplets, right? So everything cancels out. You get this one cancels with this one cancels with this one, and so on. All of them gone. And you get only that part. But now what is D to the power of K? If you want diagonal matrix to the power of anything, you're just taking diagonal elements to that power. That's it. That's how you compute it. It's just scalars into the same powers that you want. Which means diagonal matrix to the power of 1 million is just power of 1 million of each diagonal element in that matrix. That's it. This is how simple it is. All right, you don't need to worry about multiplications of all of these numbers because everything else is like zeros. You don't need it, okay? So for that computation, it will be T times D cubed, which is just diagonal elements cubed, and so on and so on. You just add in the three matrices, very simple computation. So everything you needed to do is just to compute eigenvalues, eigenvalues and eigenvectors, and then just powers of diagonal matrices and adding them together. That's it. Very simple. So any computation of polynomials of matrices is much easier in that space compared to the original matrix A. Okay, computationally much easier. And that's why we need diagonalization in general. Any questions so far? Yes.
So my question is about eigenvalue decomposition and its similarity transform.
Similarity transform, yes.
Okay, so this transform given A is equal to T, let's say D T inverse, and then from your explanation, D is the eigenvalues,
So D are eigenvalues, yes.
and then T is the eigenvectors, and T inverse is the inverse of the eigenvectors.
It's the inverse of the eigenvectors, yes.
Yes. So if you equate this to just eigenvalue decomposition, where we have eigenvectors multiplying eigenvalues, there is the extra term in the similarity transform T inverse. It's kind of confuses me. I don't know whether I get my point. It's like there's this extra T inverse term. Oh, it does not really matter.
So the overall idea goes like that. So you have all kind of possible systems of coordinates, okay? In some system of coordinates, it's more convenient to do computations. In some other systems of coordinates, it's not convenient to do computations. So that similarity transform practically takes you to a convenient system, whatever it is, right? Then you're doing computations there in that system, and then you return it back with inverse transform, which is T inverse, okay? So it's like transforming system of coordinates, doing computations there, and then doing inverse transform, and that's exactly what similarity is doing, okay, and then getting you back. Now, in our system of coordinates, it's very convenient that matrices will be diagonal, all of them, because they become kind of scalar. And you can do operations like on scalars in that kind of particular system of coordinates, which is eigensystem of coordinates, right? So in that system, matrices become scalars. In a sense, because multiplication by matrix becomes multiplication by scalar in that system of coordinates. So you're taking with T, you're taking it to that system of coordinates, and then you're taking it back with T inverse. This is kind of big picture, right? And again, this is not mathematical description of things, but this is just kind of intuition behind it, like what it does. And this is not really explaining why that particular system is more convenient than some other systems. It's a more tricky part.